All right, get ready because today we're going deep on something that'll really get you thinking, time machines.
Oh, yeah.
But before you go picturing yourself, jumping into some DeLorean, we're going way past the science fiction stuff. We're going to be exploring the theoretical and philosophical possibilities of time travel, and specifically, as they're discussed in the Stanford Encyclopedia of Philosophy.
Yeah, it's a really cool spot where physics and philosophy meet, Really makes you question how we think about time and whether we can actually change it.
Exactly.
Right.
We are not talking about Doc Brown and his inventions here, not at all. We're going deep, deep into the weeds of theoretical physics to figure out, at least on paper, if time machines could even exist.
And for a philosopher, this gets really, really interesting because it touches on these huge questions, cause and effect, free will, even the flow of time itself.
So, to kind of set the stage here, our main source is the Stanford Encyclopedia of Philosophy's entry on time machines. So, get ready, we're going to be unpacking some pretty dense concepts, but I promise we'll walk you through it, we'll have clear explanations, and maybe even a mind-bending thought experiment or two.
Yeah, the first thing we need to wrap our heads around is that the concept of a time machine in physics, it's not like what you see in movies. Forget about those Wellesian time machines, with levers and dials and stuff. We're looking at what physicists call Thornian time machines.
Oh, okay, Thornian time machines, named after
Named after the physicist Kip Thorne,
Kip Thorne, right?
who had this idea that a super advanced civilization, they might be able to mess with the fabric of space-time itself to create something called closed time-like curves, or, CTCs.
So instead of building a vehicle that travels through time, you're basically what, rearranging the universe itself to make time loops possible.
Yeah, kind of.
Whoa, okay, so that's pretty heavy. So what would make a space-time suitable for hosting a time machine? I mean, the Stanford Encyclopedia lays out three key features, right?
Yeah, yeah.
First, we need something called temporal orientability.
Basically, all that means is time has a consistent direction, a clear arrow pointing from past to future.
Okay, that makes sense. Second, we need a definite time orientation. So we got to be able to point to what forward in time actually means.
Which, that itself leads to a whole philosophical debate about what time even is. But for now, let's just assume we've got that direction figured out.
Yeah, sounds good. The third feature is a causally innocuous past. So we need a starting point in time before any CTCs even exist, right?
Right.
Like we want to see if time machines can actually create them, not just study ones that might already be out there.
Yeah, exactly. It's like starting with a totally clean slate and seeing if a time machine could be the cause of those time loops.
And physicists, they use models to try to understand this. And one example that the Stanford Encyclopedia brings up is something called
Misner spacetime.
Misner spacetime. Okay, what's that all about?
Okay, so picture this. A flat sheet, and it represents space-time. Now, as you move towards the future, the sheet, it starts to warp, starts to twist, and eventually it forms loops. Those loops, those are the CTCs.
So it's like the structure of the universe itself is folding in on itself, and that's creating these pathways for time travel.
Yeah, that's a good way to put it.
Okay, but here's the big question. If we see these CTCs, pop up in a model, can we definitely say a time machine caused them?
Well, that's where things get a little messy. Our normal understanding of cause and effect, it gets kind of wonky when you start throwing in time loops.
Right, yeah, like if something from the future could travel back and affect the past, how do we even know what caused what? It's like a chicken and egg problem, but like on this huge cosmic scale.
Exactly. And one way physicists try to deal with this is with this concept of causal determinism. The idea is that the state of the universe at any given time should completely determine everything that happens next.
So it's like a domino effect, right? One event leads to the next in this predictable chain.
Exactly, precisely. But when you bring in CTCs, things get a lot more complicated.
Yeah.
Because actions in the future could ripple back and change the past, right? Which really messes up that neat chain of cause and effect.
Yeah, it's like those time travel paradoxes where you go back in time and you accidentally present your own birth. Things get really weird.
Yeah, really wibbly wobbly. So, to understand how this affects our time machine model, we gotta think about the future domain of dependence. It's the region of space-time where events are totally determined by the initial state of the universe.
Okay, so everything in that domain, it has a clear cause and effect relationship with the starting point.
Right, but CTCs, If they exist, they'd lie outside of this domain, meaning they wouldn't be neatly determined by the initial state. They'd be like, wild cards just thrown into the deck.
So even if we had, like, a perfect understanding of the universe at a certain time, we couldn't predict for sure whether CTCs would just pop up.
Exactly. Strict causal determinism just doesn't work when you're dealing with the possibility of time travel. So physicists have been looking at other approaches, like requiring CTCs to be adjacent to the future domain of dependence.
Adjacent. Okay, so you mean like they can't just show up out of nowhere. There needs to be some connection to the initial state of the universe.
Exactly. One way they tried to define this adjacency was by looking at causal curves that end in the time travel region. But they have no defined beginning point. Think of them like paths that just loop back on themselves forever, representing endless time travel.
Okay, so these paths, they might twist and turn, but they always lead back to that time travel region.
Right, and the initial idea was that these paths, if they ever left the time travel region, they should intersect the initial time slice, the moment before the time machine is even switched on.
So there's a connection, a pathway from the time travel region back to the very beginning.
Right, but this requirement, it actually turned out to be too strict. It ruled out a lot of models that could maybe host time machines. It's like saying you can't draw a circle unless it touches a specific point on the paper.
So they needed a more, I guess, flexible definition of adjacency that wouldn't totally shut down the idea of time travel. What did they end up coming up with?
Well, they shifted their focus to time-like curves instead of just any causal curve. These are paths that things with mass, like us, can travel through spacetime.
So it's like saying, instead of looking at every possible path, we're only interested in the paths that, a spaceship or a person could actually take.
Exactly, and this opened up the possibility of time travel in models like Misner spacetime, where every time-like curve coming out of the time travel region does eventually intersect the initial time slice.
So there's a pathway back to the beginning, but only for things that have mass and travel slower than light.
Right, but as always, there's a catch. This relaxed requirement, it also ended up being a bit too permissive. It allowed for some scenarios that didn't really fit our intuitive idea of a time machine.
Okay, like what? Give me an example.
All right, picture this. You've got a perfectly flat sheet. It represents a space-time with no time travel at all. Now, imagine cutting out a few tiny circles from the sheet, creating holes.
Okay, I'm picturing it, a flat sheet, some holes punched out of it.
Now imagine stitching the edges of those holes together in a specific way that creates a region with CTCs.
So we've basically just made time travel by manipulating a space-time that originally had no time travel at all.
Exactly. This is an example of what's called Deutsch-Pulitzer spacetime. But the problem is, up to a certain point in time, this spacetime looks exactly like the original flat sheet. So how can the initial state, which seems perfectly normal, be responsible for suddenly creating a time travel region?
It's like saying you took a normal piece of paper, and without doing anything to it, a Mobius strip just appeared. Something doesn't seem right.
You're totally right. It feels like we're stitching in time travel after the fact, rather than it naturally coming from the initial conditions.
So while adjacency is important, it's not enough to guarantee that we're looking at a real time machine. What other criteria did physicists come up with?
Well, one way to get rid of those cheating scenarios is to focus on those holes we made in space-time. Maybe a real-time machine needs a space-time that's smooth and continuous, with no holes or tears.
Okay, so maybe we need to add a no-holes rule to our definition of a time machine.
That's one way to think about it. Stephen Hawking, he proposed something called a compactly generated Cauchy horizon as a more strict condition.
Whoa, break that down for me. Compactly generated Cauchy horizon.
Okay, so remember the future Cauchy horizon we talked about? That boundary between the predictable and unpredictable regions of space-time?
Yeah.
So Hawking's idea was that for a time machine to be possible, the curves creating this horizon, they shouldn't come from singularities, those points where space-time breaks down or come in from infinity.
So they got to have a well-defined origin within the space-time itself, not from some weird outside source.
Exactly, and this nicely rules out that Deutsch-Pulitzer space-time. Because those holes we cut out, they act like singularities, messing up the smooth structure of space-time.
So compactly generated Cauchy horizon, that seems like a pretty reasonable requirement for a real, genuine time machine. But does it guarantee that the initial conditions of the universe are responsible for making CTCs?
Well, that's the big question, and it leads us to one of the most mind-blowing parts of all of this, the idea of future branching.
Future branching, does that mean Like alternate timelines or multiple possible futures.
Pretty much. It's the idea that even with, the laws of physics and a specific set of initial conditions, there could be lots of ways the universe could evolve. Think of it like, a tree trunk branching out into different paths.
I'm following you. Okay, so how does this relate to time machines?
So when you've got a Kachi horizon, the future becomes less deterministic. There might be different ways to extend the space-time beyond that horizon, different branches of possible futures.
And some of those branches might have CTCs, while others don't.
Exactly. So even if the beginning state of the universe leads to a Kachi horizon, it might not guarantee those CTCs. It just opens up the possibility.
So a time machine might not be like a direct cause of CTCs in the way we usually think about cause and effect. It's more like a catalyst that makes them possible, like rolling the dice, but on a cosmic level.
That's a great way to put it. And it takes us to another fascinating piece of this whole puzzle. But you know what? Before we get into that, let's take a break and come back for part 2 of our deep dive. So, up to this point, we've been mostly talking about time machines in the world of classical physics, specifically general relativity.
Right.
But to really get a grasp on what's possible, we have to bring in the quantum world.
Right, because when you start talking about bending and twisting space-time, you're bound to bump into all the weirdness of quantum mechanics.
Exactly. And when we're talking about combining quantum mechanics and gravity, there's a few levels of how much quantum we need to think about.
Okay, break it down for me.
So the first level is what's called quantum field theory on curved spacetimes. Basically, it takes a pre-existing spacetime, as described by general relativity, and looks at how quantum fields act within that background.
So it's like we're taking the stage set from classical physics and letting the quantum actors do their thing on it.
Perfect analogy. One really famous example is the Unruh effect, which says that a quantum field, it'll appear to heat up when it's accelerating through spacetime, even in a vacuum.
Whoa, so even if space-time itself is empty, quantum stuff can still get heated up just by moving through it.
Exactly. It shows how deeply connected quantum fields, motion, and the structure of spacetime really are.
Okay, so that's level 1. What about level 2?
Level 2 is where things get even more interesting. It's called semi-classical quantum gravity, and it tries to account for the fact that quantum fields don't just exist in spacetime, they can actually influence its curvature.
So now, the quantum actors can start messing with the stage set itself.
Precisely. Instead of just assuming a fixed spacetime background, we now have to consider how the energy and momentum of quantum fields can actually warp and bend spacetime.
And in general relativity, that warping of space-time is what creates gravity, right?
Exactly. So in semi-classical quantum gravity, we're basically trying to understand how the quantum world can actually influence the structure of spacetime, and maybe even create those CTCs we've been talking about.
So maybe, just maybe, we could manipulate quantum fields to create those time loops and build a time machine.
That was the hope, and some early research actually seemed to suggest that quantum fields might prevent time travel.
Wait, really? How so?
Well, physicists found that in some models, the energy density of quantum fields would become incredibly large near the Kachi horizon.
That boundary between the predictable and unpredictable regions of space-time, right?
Right, and that huge energy density, according to Einstein's equations, would create this insanely strong gravitational field. Essentially, space-time would become so warped that it would pinch off the time travel region, preventing those CTCs from forming.
So it's like there's a built-in safety mechanism. The universe is trying to protect itself from the paradoxes of time travel.
It's a beautiful idea, but like most things in physics, it's not quite that simple. Later studies found exceptions to this rule. There were scenarios where quantum fields, even near the Kachi horizon, wouldn't necessarily create that huge energy density.
So the quantum safety net might have some holes in it after all. Maybe there's still a chance for building a time machine.
Maybe, but then another theorem came along, kind of threw a wrench in the works, the K-Radzikowski-Wald theorem, KRW theorem for short.
All right, tell me about this KRW theorem.
So remember how we said in semi-classical quantum gravity, physicists calculate the energy and momentum of quantum fields to see how they affect spacetime?
Yeah, like figuring out the recipe for how space-time will warp based on the quantum ingredients.
Right. Well, the KRW theorem proved that this recipe, at least how we understand it now, breaks down at the Kachi horizon.
So we can't accurately predict how quantum fields will behave right at the edge of a time travel region.
Exactly. It suggests that semi-classical quantum gravity, our best attempt at combining quantum mechanics and gravity, might not be the right tool to understand what's happening in those really extreme regions of space-time.
So back to the drawing board for the time machine enthusiasts.
Not necessarily. The KRW theorem is super important for understanding the limits of our current theories, but it doesn't definitively rule out time travel.
What do you mean?
Well, for one thing, it relies on that compactly generated Cauchy horizon idea that Hawking used, the assumption that the horizon can't come from singularities or come in from infinity.
And we already talked about how that might be too narrow of a definition for a time machine. There might be other ways to create CTCs.
Exactly. The other possibility is that the KRW theorem might just be showing us the limitations of semi-classical quantum gravity itself. Remember, it's not a complete theory of quantum gravity, it's just an approximation.
So maybe it's breaking down not because time travel is impossible, but because our current tools aren't good enough to handle the extreme physics involved.
That's one way to think about it. Some physicists have even argued that the breakdown of semi-classical quantum gravity near the Cauchy horizon might be a sign that we need a completely new theory of quantum gravity to understand what's really going on.
A theory where time travel might actually be possible. So it sounds like the KRW theorem, while a big challenge, doesn't completely shut down the dream of time machines.
Absolutely not. It just shows how much we still don't know about how quantum mechanics and gravity work together. It's a reminder that we might need a radical shift in how we think about space and time to really understand the possibilities.
Okay, so we've explored the first two levels of quantum involvement. What about level 3, a full-blown theory of quantum gravity?
Now we're getting into some really uncharted territory. Right now, the main contenders for a complete theory of quantum gravity are loop quantum gravity and string theory.
And I've heard those are both incredibly complex, really mathematically challenging theories.
They are, but they offer some really interesting hints about the nature of space-time at the Planck scale, the smallest possible length scale where quantum effects are dominant over gravity.
And what do those hints say about time travel?
It's still very much an open question. Both loop quantum gravity and string theory have had some success in resolving certain types of singularities, the ones that plague classical general relativity.
Those points where space-time breaks down, like at the center of a black hole.
Right, but whether they can solve the potential paradoxes of CTCs and make time travel a reality, that's still unknown. It's an active area of research, and physicists are exploring these questions with a lot of enthusiasm.
So we might have to wait for a fully developed theory of quantum gravity to know for sure if time machines are possible.
That's probably true. But in the meantime, there's another less mainstream approach to quantum gravity that offers an interesting perspective on time travel: causal set theory.
Causal set theory, what's that about?
It's a fascinating approach that models space-time not as this smooth, continuous fabric, but as a collection of discrete points connected by causal relations.
So instead of like a flowing river, it's more like a bunch of individual water droplets linked by the order they splash.
Exactly. And what's really interesting is that causal set theory builds in the arrow of time from the very beginning. The causal relations between those points define a direction from past to future.
And since those causal relations are fundamental, built into the structure of space-time, maybe that rules out the possibility of CTCs in time travel.
That's one interpretation. It suggests that time travel might be fundamentally incompatible with the underlying structure of space-time, as described by causal set theory.
So, while we don't have the definitive answer from a complete theory of quantum gravity, causal set theory offers this interesting possibility that time travel might just be impossible, like it's baked into the very fabric of reality at the Planck scale.
It's a fascinating thought, but even if causal set theory turns out to be wrong, there's still the question of whether we could actually build a time machine, even if the laws of physics allowed it.
Right, because even if time travel is theoretically possible, it doesn't mean we'll ever have the technology or know-how to make it happen.
Exactly. Building a time machine would probably require manipulating energy and matter on scales that are way beyond anything we can do right now. We might be talking about harnessing the power of black holes or creating those hypothetical wormholes, tunnels through space-time that could connect distant regions.
And we're not even sure if wormholes are physically possible, let alone something we could control.
Right. So even if the laws of physics allow time travel, actually building a time machine might be practically impossible, at least with what we know now.
But hey, who knows what the future holds, right? Maybe someday a super advanced civilization will figure out how to make time travel a reality. Then what? What would the implications be?
That's where the philosophical side of this discussion really comes into play. If time travel was possible, it would force us to rethink some of our most basic beliefs about free will, morality, the meaning of history.
It'd be like opening Pandora's box. If we could change the past, would it still be our past? Would our actions in the present even matter if they could be undone by someone from the future?
These are some really big questions, and they highlight how deeply connected physics, technology, and our understanding of ourselves really are. Even if time machines stay theoretical, just exploring these questions can help us understand the nature of time, causality, and the human condition better.
So, whether or not time machines ever become real, this deep dive has been a wild ride. We've learned about the complexity of space-time, the challenges of defining causality, and the really deep philosophical questions that come up when we talk about time travel.
It's been a true exploration of the boundaries of physics and the limits of our imagination. And who knows, maybe someday we'll look back at this conversation as the first steps towards a future where time travel isn't just science fiction anymore.
Until then, we'll keep thinking about the mysteries of time and the possibility of journeys beyond the present. Thanks for joining us on this deep dive. Welcome back to our deep dive into time machines. It's been a wild ride so far, hasn't it?
It really has. We've covered so much ground already.
I know, right? But there's one key question we need to circle back to. What does it even mean for a device to be responsible for creating those time loops, the CTCs?
Yeah, it's a tricky one.
It's like, how do you even define responsibility when you're talking about something as mind-bending as time travel?
Exactly. We're not just saying that CTCs exist somewhere. We're trying to figure out if a device, a time machine, can actually make them happen.
So it's not enough to just find a universe with time loops. We need to know if those loops are like a natural part of that universe or if they're a result of something deliberately messing with space-time.
Exactly. And one of the most interesting ways to define time machines focuses on this idea of extending space-time. Imagine you have a region of space-time, like a snapshot of the universe at a specific moment, and you try to grow it forward in time.
So it's like taking a seed and seeing what kind of plant it could grow into, depending on, the environment and stuff.
That's a great analogy. In the context of time machines, we're curious about whether every possible way of extending a specific space-time while still following the laws of physics will always lead to CTCs.
So it's not just one specific future that has time loops, but every single possible future that could come from that starting point. That would be some pretty strong evidence that a time machine is at work, right?
It would suggest that the appearance of CTCs is kind of baked into the fabric of space-time itself, not just a random feature of one timeline.
Okay, I get that, but didn't we run into a problem with this idea earlier? Something about holes in space-time messing things up?
You're thinking of Krasnikov's theorem, which seemed to say that for any space-time with CTCs, you could always find another one that extends the first one, but without any CTCs.
Right, it felt like a cheat. Like saying, sure, you've got time loops in your universe, but over here in mine, which is just as real, there's no such thing.
Yeah, and as we discussed, Krasnikov's theorem often relied on creating those holes in space-time, those points where the fabric of reality breaks down.
Yeah, it felt like we were just patching things up to make the time loops disappear, not a very satisfying explanation.
Right, so physicists have been trying to find ways to strengthen the idea of space-time extensions to rule out those artificial hole-punching tricks.
So we need a way to make sure that the extended space-time is hole-free, a smooth continuation of the original one.
Exactly, and there are a few different mathematical ways to capture this idea of hole-freeness. One way focuses on the causal structure of space-time, making sure that the relationships between events, what can influence what, stay consistent as we extend the space-time.
So like making sure that the threads of cause and effect don't get all tangled up as we're expanding the fabric of reality.
Exactly. Another way focuses on the geometric properties of space-time, making sure that things like curvature are well behaved and don't suddenly become infinite or jump around crazily.
We want to avoid those singularities, those points where space-time breaks down.
Exactly. And the hope is that by adding these stricter no-holes conditions, we can find examples of spacetimes where every single hole-free extension will always lead to the creation of CTCs.
That would be pretty convincing evidence for a real time machine, wouldn't it? A time machine that doesn't rely on any math tricks or loopholes.
It would. It would suggest that those CTCs are a fundamental consequence of the laws of physics, given certain initial conditions.
Okay, so now we have a better understanding of how physicists are trying to define time machines in a way that considers all the complexities of causality and space-time extensions. But even if we find such a model, does that mean building a time machine is actually possible? Could we really do it?
Ah, that's the big question. And it's one that goes beyond theoretical physics and into the realm of engineering and technology.
Because we're not just talking about drawing diagrams on a whiteboard. We're talking about manipulating the very fabric of space-time.
Exactly. We might be talking about generating super strong gravitational fields, harnessing the power of black holes, or even creating those theoretical wormholes, tunnels through space-time that could connect faraway places.
And we're not even sure if wormholes are even physically possible, let alone something we could control.
Right. So even if the laws of physics say time travel is okay, actually building a time machine might be impossible, at least with what we know now.
Yeah, but who knows what the future holds, right? Maybe
Okay.
someday some super advanced civilization will crack the code and figure out how to make time travel real. Then what? What happens then?
That's when the philosophical side of all this becomes super important. If time travel were possible, it would force us to rethink some of our most basic beliefs about free will, morality, the meaning of history.
Like opening Pandora's box, right? If we could change the past, would it even still be our past? Would our choices in the present even matter if they could be undone by someone from the future?
These are big, profound questions, and they show how deeply connected physics, technology, and our understanding of ourselves really are. Even if time machines stay theoretical, exploring these questions can help us better understand the nature of time, causality, and the human condition.
So whether or not time machines ever become a reality, this deep dive has been a truly mind-bending journey. We've learned about the complexities of space-time, the challenges of defining causality, and the deep philosophical questions that come up when we talk about time travel.
It's been a real exploration of the boundaries of physics and the limits of our imagination. And who knows, maybe someday we'll look back at this conversation as the very first steps towards a future where time travel isn't just science fiction anymore.
Until then, we'll keep pondering the mysteries of time and the possibility of those journeys beyond the present. Thanks for joining us on this deep dive.